We've seen our LTI systems and that they can transform our input of x of t to an input of y of t. And there is another operation that is very important to these systems because they help us in these computations. And this is called convolution. Which has an operator with a star. And the convolution says something about how one function influences the other function into a new function. When I first heard it, it was also a very difficult thing for me to grasp, to understand. But I hope that I can help you understand it now better, because I also have some visualization tools for you. So if we convolute two functions, what does that mean? It means that we're going from minus infinity to infinity of our function of s multiplied with our function t minus s derived over s. This is what convolution does. We're shifting one surface over the other and look at their shared surface. Before I will show you some nice visualization, I want to tell you that if we convolute two functions, it doesn't matter in what order we convolute them. It doesn't matter which function, what other function we convolute first. It is the same as multiplication with this t g and then convoluted with j. That does not change anything. It is also distributive, meaning that if we have something like this, it is the same as if we would convolute our g function and convolute our j function. These are just some properties. Of course, also, I forget, if we have a scalar, we multiply this with. It doesn't matter if we do it afterwards or before we start convoluting. So you can really actually equate it to multiplication, because a lot of properties also hold for that. Now, I want to show you a visualization of what convolution means. So let's say we have a function which is just a square, and another function that is also a square, and we convolute those two functions. What happens? The next thing happens. So we see that we have two boxes, the red one and the blue one, and the red one is our g function. These videos can be found on Wikipedia, and this red one is our g function, which shifts over the blue one, and the new function is the black line which will appear, which shows their shared surface. So here they start to overlap, and you see that the black line appears because the value of the black line shows what their shared surface is. And when they are exactly on top of each other, the black line is of course exactly their height as well. And it will shift all over the other surface, leaving us with a new function which looks like a triangle. Just like that. Even shown you with another function. One function here is our e to the power minus t multiplied with a step function, and left is of course another square function. And if we shift these two over each other, we again look at the shared surface, and the shared surface, what the t value is, at what t value that will appear, depends on the t value in the second function. And as you see, the shared surface is our new y value. So we obtain a new function. This is what convolution does. There's a lot of uses in probability theory as well, with continuous distributions, as well here with LTI systems. They are used in electrical engineering and a lot of other areas. So what are some properties of convolution with some specific functions that we have? One of the properties that we have is when we have a function convoluted with a delta function that is shifted a bit. Well, this results in our original function, which is shifted a bit. And if our difference time is 0, then of course we just get our original function back. And if we convolute our function with a step function, this is actually equal to an integrator, where we're just looking at the integral of our function up until a certain point. Well, once again, why is this important for us? Why are this convolution operation, why is it nice for us? Well, let's say we have our system T, which is a very complex system. It takes a lot of operations and computations to actually solve this. And our input is also not very easy, so this can take a long time. But if we put in our impulse function, which is very standard, very straightforward, it just exists on one point. If we look at how this function changed, so we look at the output, if we convolute our function, our input function, with a delta function, just a delta function, we get our original function back. But if we look at how our delta function has changed and convolute that with our input, we actually get our output. How the function should change through the system is now stored in our impulse response, which is amazing. We just need one impulse response from the system, and then we can just throw the system away because we know what the system will change if we put it into a function. Put a function in, because it is stored in our impulse response. This is nice. So let's test that out. Let's get an example running. So we get an example. Remember, our output is equal to the input convoluted with our impulse response. So let's say our input, not f of t, x of t. Let's say our input is equal to e to the power t, and our impulse response is equal to u of t. Well, if we convolute these two together, what do we get? We get the integral of minus infinity to infinity of e to the power of s multiplied with u to the u t minus s ds. And a step function always changes your integral. Let's take a look here. When does a step function turn 0? Well, we know if t minus s, if this is bigger or equal than 0, then this function will output a 1. Otherwise, it will output a 0, and everything times a 0 is always 0. So we need to know when this step function actually exists. We can rewrite this into minus s is bigger or equal than minus t, or in other words, s is smaller or equal than t. So for every s value that is smaller than the t, we will get a value. Otherwise, we will always multiply with a 0. And this is one easy way to always look at your step functions if you need to integrate them, how they will change your boundaries. Because right now, we know that our s value cannot run up until infinity. It can actually run up until t, because after that it will be multiplied with 0. So we know in this case, we get that u is always 1, so we can just remove that from our equation. We're just left with e to the power of s. In one case. In the other case, we get 0 if if s is bigger than t. And here we get it if s is smaller or equal than t. So if we even work this out further, we get e to the power of s is still e to the power of s. We fill in t and minus infinity. if we fill that in, we get e to the power t minus e to the power minus infinity. And e to the power minus infinity is actually 0. So we get back e to the power of t. So, because we have these cases, let's write these cases again. What is the output of my y function? Because this is x convoluted with h. We get e to the power of s for all s values smaller or equal to t, or we have no s anymore. We have t if t is bigger or equal than 0, and 0 if t is smaller than 0. And why is that? Because s needed to be smaller than t, and we have filled in t for s. So we know that since s should always be smaller than t, t should be at least 0. And since this is our answer, we just actually have two cases, and with these cases, we get the following. We get that this is actually equal to e to the power t minus u multiplied with a step function. If we do not want to write it in cases, we just want to write it like this. And this is actually our input again. And why is that? Because if our impulse response is actually the step function, that means our system integrates our input, and the integral of e to the power t is of course e to the power of t. So this is a simple convolution example, and in the following videos we will look at some more difficult functions to convolute with each other.